Chapter 8 Deadlock. Chapter Objective illustrates how deadlock can occur when mutex locks are used. Define the four necessary conditions that characterize deadlock. Apply Branker algorithm for deadlock avoidance. Apply the deadlock detection algorithm. Our low approach for recovering from deadlock. System model. System consists of resource type R1, R2, 2, RM, CPU cycle, memory space, I/O device. Each resource type Ri has WR instance. Each process utilizes a resource for a resource as follows: request, use, release. Deadlock with semaphore. Data semaphore S1 interest to 1 semaphore S2 interest to 1. Two processes P1 and P2. P1 with S1 with S2. Deadlock characterization. Deadlock can arise if four conditions hold simultaneously mutual execution. Only one process at a time can use a resource, hold and wait. A process holding at least one resource is waiting to acquire additional resource held by other processes. No preemption. A resource can be released only voluntarily by the process holding it after that process has completed its task. Circular with there exists a set of waiting processes such that P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. Resource allocated graph, a set of vertices V and a set of 8E. V is partitioned into two types. P, the set consisting of all the processes in the system. R, the set consisting of all resource types in the system. Request 8, directed 8, PI to RJ, assignment 8, directed 8, RJ to PI. Basic facts. If graph contains no cycle, no deadlock. If graph contains a cycle, if only one instance per resource type, then deadlock. If zero instance per resource type, possibility of deadlock. Method for handling deadlock. Ensure that the system will never enter a deadlock state. Deadlock prevention. Deadlock avoidance. Deadlock prevention. Multiple execution, not requiring for shareable resource, must hold for non-shared resource, hold and wait, must guarantee that whenever a process requests a resource that it does not hold any other resources. No preemption. If a process that is holding some resource request another resource that cannot be immediately allocated to it, then all resources currently being held are released. Circular wait implies a total ordering of all resource types and requiring that each process requests resource in an increasing order of implementation. Circular wait in validating the circular wait condition is most common. Deadlock avoidance, simplest and most useful model requires that each process declares the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Safe state. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. System is in safe state if there exists a sequence of all the processes in the system such that for each PI the resources that PI can still request and can be satisfied by currently available resource plus resources held by all the PJ with J less than L. Basic phase. If a system is in safe state, no deadlock. If a system is in unsafe state, possibility of deadlock avoidance ensure that a system will never enter an unsafe state. Avoidance algorithm. Single instance of a resource type. Use resource allocation graph. Multiple instances of a resource type. Use the Banker algorithm. Resource allocation graph seismic climb edge indicate that process Pj may request resource Rj represented by a dashed line. Climb edge convert to request edge when a process requests a resource. Banker algorithm. Multiple instances of resource each process must period climb maximum use. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. Data structure for Banker algorithm. A variable vector of length m if a variable j maxed in allocation need deadlock detection allows system to enter deadlock state. Detection algorithm recovery says single stand of each resource type maintain wait for graph need are processes. periodically invoke an algorithm that searches for a cycle in the graph if there is a cycle that exists at deadlock. Detection algorithm let work and finish be vector of length m and n respectively. Find an index I such that both finish request. If no such I exists, go to step 4. Work equal work plus a location. Finished equal false. Detection algorithm uses when and how often to invoke depending on how often a deadlock is likely to occur. How many processes will need to be rolled back. If detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we would not be able to tell which of the many deadlock processes caused the deadlock. Recovery from deadlock process termination. Abort all deadlock processes. Abort one process at a time until the deadlock cycle is eliminated. In which order should we choose to abort? Recovery from deadlock. Resource preemption. Selecting a victim. Minimize cost. Rollback. Return to some safe state. Restart process for the state. Starvation. Same process may always be picked as victim. Include number of rollback in cost factor.